let us take one example for doing this Archimedes principle. Of course, it is very straightforward only, but now let us suppose that okay, there is a, it is known as, there are things called buoys. I mean, it is one kind of way of jacking up a, it is a sphere, a hollow sphere, okay. It is a way of jacking up some weight. Now, suppose that it is carrying a, it's put in water to carry some weight, let us say of mass m, all right. Now, the details given are this is a spherical buoy and spherical buoy is used for carrying an instrument, means it is carrying, it is floating with a weight on it equal to mass m. Now, the buoy is made of a 3 millimeter steel plate, okay. It is not a solid sphere, then of course it will just sink. It is a steel plate, 3 millimeter steel plate. It is a 3 millimeter steel plate, so it is just 3 millimeter thick. Now, your and it has, and your question is, and it is that steel plate has a steel has a density of rho s, okay, rho of steel. Then now your question is, what should be the diameter of this to support the weight m? What should be the diameter of this sphere? If so, obviously the sphere will have an outer diameter and an inner diameter. Outer diameter is, let us say d0, inner diameter will be d0 minus 3 into 6, d0 minus 6. It is 3 millimeter thick, so 3 minus 3. I mean d0 minus 3 minus 3, so d0 minus 6, right. So, that much of inner diameter it will have. So, the question is this, what should be the diameter for the whole thing not to sink or to float like that. Okay. Now, we will proceed like this. In the classes mostly I give these kind of problems as homework, but here since I cannot, I will just do the problem. So, the first of all, the volume of the submerged half sphere, the volume of this submerged half sphere is a half sphere. So, it is half of 4 by 3 pi d0 cube, okay. This is the volume of the total volume of that submerged half sphere, okay. And now, first let us find what is the mass of steel, means that, is there a problem? 4 by 3 pi r cube. Is it 4 by, why is it written? Okay. 4 by 3 pi, yeah, I think it is 4 by 3 pi r cubed, but they have done here as, yeah, I think I also remember it is 4 by 3 pi r cubed, that is the volume of a sphere, right. Okay, then it will be, so I will write it as, instead of d0 let us write it as r0, 4 by 3 pi r0 cube. So, half of that will give you the volume of that half sphere. Now, let us find the mass of steel, mass of the spherical steel. It is only a shell, okay, remember. So, this mistake they have done it throughout, it is always done as 4 by 3 pi d cubed, it is 4 by 3 pi r cube, yes. So, rho of steel into 4 by 3 pi into r0 cube, this will give you the total volume minus r0 minus 0.003, it is actually 3 millimeter, the other one is all in meters. So, 0.003 the whole cube, right. This is obvious. This is the mass of the steel, okay. Okay. So, so the total mass that the spherical buoy is carrying is this m, which is the mass of that instrument, plus this mass of spherical spherical steel. Okay. So, you will have rho s into 4 by 3 pi. Okay, I have to change this r0 cube. Okay, when you are doing this, it's written as d0. Okay, in that book, it's actually r0 only. R0 cube minus r0 minus 0.003 the whole cube plus m will give you the total mass that the system is carrying. It's equal to the weight of the liquid displaced, or it's equal to rho w into half 4 by 3 pi r0 cubed. The only thing to know in this, I mean, it's not complicated at all, it's a very simple problem. Only thing to know is, which, as you can see here, which are the weights that you have to have on the right side, left side, which is the volume that you need to have on the right side, left side. That is the only confusing thing in this problem. So, means to find out the mass of steel, you need to know what is the volume you have to take. That is of course straightforward, you know it is only a spherical shell. The volume on the left hand side, which we are talking about, what volume is it? It is not the volume of that spherical shell anymore, it is the total volume. Means if you have this is, let us say this is the sphere that is in the, so this much is inside, even though this steel is only here, the volume that you need is this, okay, the total volume, everything, the whole volume inside you need. So, that if you know, then of course, this problem is very simple. Then rho w into half 4 by 3 pi r0 cubed. Now, of course, this becomes a cubical equation and you just solve for r0. Okay, this is the problem. So, you just solve for this, you can solve this problem, and that is your first problem in this. Next one we will do it after we do the GM part. Okay. Now, now we come to another important concept in naval architecture. It is known as the concept of, I will shift here. We come to a concept known as, if you look at that again, if you look at that picture again, yes, you will see at the top we are talking about something called M as a metacenter. This is the concept that we are going to work on for probably the rest of this lecture at least. So, this is known as a metacenter. I will explain what it is. Now, let us suppose that you have a submerged half body and or that at G the weight W is acting downward, at B0 the weight again delta, same delta equals W, W equals delta is acting upwards. Just one more thing in this is, this bottommost point in the ship, okay, is what we call as keel, KEEL, and always the bottommost point is given by the symbol K. So, in this figure also you will see M, I will explain, G is the center of gravity, B is the center of buoyancy, and K is the keel. It is always the bottommost point, and always you start the coordinate system like this, you call K to be 0 and K to be Z equal to 0, and from there Z starts increasing upwards. Okay. So, this is the coordinate system always we are going to follow. Now, okay, now we have the system, we have G, B0 and K. Now, let us suppose that the body is tilted somehow, that is, suppose that I moved G to a new point, or let us say it is tilted due to wind. It means I am not changing the G as such, means ship was like this, let us say a wind acted on the ship and the body tilted. Okay. So, we are not going to change G as such, let us leave G there, and the body tilted like this because of wind. Now again I am not going to draw the body as tilted, I am going to draw the waterline as tilted. That is why this W1 L1, it is usually written as, okay, here they have written as W phi L phi. And as I told you before, always the heel angle is written by the symbol phi, okay. This is phi, and the trim angle, which we are not doing at all this now, is written by theta. So this is phi in that figure, this is phi, okay. So this is the angle by which the body has heeled, so that is phi. Now because of this heeling, more volume has come on one side, less volume on one side, as a result B will shift. The center of buoyancy has to shift, because more where there is more volume, it will shift to that side. Let us say that B has shifted to this point B phi. Now suppose I draw a vertical along this B. That means from B I have drawn a perpendicular to W phi L phi, which will be a vertical now. So that vertical, and initially there was this B0, let me draw a vertical here also, okay. I hope you understood what those two means. Initial point, figure is a little clogged there, but you can see here at this B phi, B0, I am drawing a vertical. This is a vertical going through G, it goes up. Then because of the tilting of the body, B0 has gone to B phi, from where I draw another vertical, right. Now these two verticals will intersect at a point somewhere at the top. That point is known as a metacenter, always denoted by the symbol M, okay. Now what do you see in this figure? As now you see that W phi L phi is like this, that means what? The body has tilted like this, and then look at the direction of the moment that is produced as now B0 has gone to B phi, okay. Now look at, now see how the because of this new delta at B, what is the direction in which is trying to tilt the ship? It is trying to tilt the ship B, it is here, it is like this, it is trying to tilt it like this now. Fix it here and see, it is trying to tilt it like this now, okay. That means it is trying to bring it back to the original position, bring the ship back to the original position. So it is a kind of stable equilibrium. So this is the metacenter as it is drawn for a stable body, not stable body, for a stable equilibrium situation. Okay. Now now B can shift in this figure, B can shift in such a way, let us say it shifted to somewhere at this point, such that this vertical, this is the vertical again, I am drawing from B, is shifted, is at M here, okay. Okay. Now let me see, now G will act here, delta, no, G is the weight, G the weight will act here, and here it will act. Now look at this figure, there is a slight difference between this figure and the previous figure, that is, it is just a difference in the position of B, okay. It might be due to different things, that is, could be due to the shape, mainly it is due to the geometry of the ship, okay. or it could be due to the distribution of weights. You can put the weights in such a way that it can be this way or the other way, but this figure, as you can see, is slightly different from the previous figure. B went in such a point in the previous case such that the righting moment the moment that was produced as a result of the movement is trying to bring it back to the original position. Now look at this figure. This also ship has tilted in the same direction as before, but this case you are seeing this moment is trying to act like this again. It is trying to increase the tilting of the ship. It is trying to make it unstable. So this is a case, again this M is the metacenter. So this is a case of unstable equilibrium. Now what do we derive from these two figures is that if you have the system such that because of tilting, if the metacenter is above the center of gravity, there is obviously you can see the two of them. Look, if you look at the two, you will see the difference is that if the metacenter is above the center of gravity, you will have a stable equilibrium. If you have the metacenter below the center of gravity, you will have unstable equilibrium. Okay, this is the condition for stable and unstable equilibrium. Now this distance Gm is known as metacentric height. And so I think this figure, yeah, yes. If you look at this figure, you see the different terms that we need. That is, first is Gm. As you can see, it is the distance between G and M, Gm. Now next is Bm. So you are going from for our later studies, we will need all these 4 points actually, M, G, B and K. All 4 are important. So you are starting the coordinate system from K upwards, Z. So you have M, G, B. You have between the distance between G and M, Gm, distance between B and M, Bm, and Km, Kb, Kg, like that. Kg is the what we call as a vertical center of gravity. Okay, Kg is the vertical coordinate of the center of gravity. Kg is the vertical coordinate of center of gravity. Kb is the vertical coordinate of the center of buoyancy, Cb, and you automatically have your Bm, and this Gm is known as metacentric height, and Bm is known as metacentric radius. All these terms are equally important. We will see the next section is actually dealing with the derivations of all this. Now what did we see as the condition for stable equilibrium? We saw that G should be below M, or M should be above G, which can be written in a mathematical form as, since we are calling K as 0, we say that Gm should be positive. If Gm is negative, then it's M is below G. So the condition for stable equilibrium is that Gm should be greater than 0. This again is a very, very important concept, and they always ask this in the Viva. So what is the condition for stable equilibrium? Is the condition is that Gm should be greater than 0. This is the condition for it to float upright, or for the thing to come back to the original position. If it is otherwise, it will just capsize if you give it a small push. Okay, this is known as the condition for stable equilibrium. Then of course these formulas hold, that is, this is also important, just you have to remember it for the exam. Gm is equal to Kb plus Bm minus Kg. I mean, this is just geometrical, you just look at this, you will find out Gm is equal to Kb plus Bm minus Kg. Okay. Wait a minute, Kb plus Bm, yes, Kb plus Bm minus Kg, all right, it is just coming from that, and the condition is Gm should be greater than 0. Okay. And just a couple of points which you of course will know. In some senses you can say this, the center of buoyancy will always move in the same direction as the waterline, means if the waterline moves up, obviously because more volume has come in, it has to go up only, the B will go up. So, that is what it is showing here, because the center of buoyancy has moved up, I mean because the waterline has moved up, it has gone from WL to WL1, more volume has come inside, that obviously that B has to go up, and therefore, it has gone up to B1. Okay. And the other thing is about G, that is the center of gravity. If you add a weight in one point, G will always move towards that point, not it will not go reach that point, that is not the meaning, it will go in the direction of that point, because you are adding a weight there, it is just common sense. Okay. Just, and same way G moves away from the weight removal, if you remove a weight from a point, it will slightly move away from that point, and it is the same thing with weight shift. If you shift a weight from one point to another point, it will move in the direction of that shift. This I will just wait for a minute, but this is the same thing. So, you are having the condition of positive stability. So, you are having the metacenter is located above the ship's center of gravity. Now, as the ship is inclined, I will tell you what is a righting arm. Righting arm is created, which tends to return the ship to its original. I mean, we have already seen what is a moment produced, we have not quantified it, means we have not given you the mathematical expression for that arm, I will do that. Anyway, that gives you, that tells you that this arm, the moment tends to bring the ship back to the original vertical position, same position, that is positive stability. Then between the two stabilities you can have, there is, suppose that G and M coincide, that is very rare case, but such a thing suppose that you have it, mathematically it is possible. So, G and M absolutely coincides, G and M, and you will be like this, that is the metacenter and the ship's center of gravity are in the same location. Now, as the ship is inclined, nothing happens, there is no moment, that means there is nothing tending to bring it back to the original position, there is nothing tending to capsize it either, it is just remaining there as such, it is in the intermediate state, that is the state of neutral stability. And the last one is the state of negative stability. You see here that the M is below the G, and the ship's center of gravity is located above the metacenter, and as the ship is inclined, negative righting arms called upsetting arms are created, which tend to capsize the ship. Okay. All right. Then now something you definitely know, it is just a small concept on moving a mass and what happens to the center of gravity as a result. Now, suppose that you have now, let us assume that you have a mass m1 at x1 and you have a mass m2 at x2. Now, the center of gravity of the system is given by xg is equal to okay. This is the definition for the center of gravity of the system. Now, suppose that I move this mass m2 to the new point, slightly I move it to the x direction by a distance d, m2 is now here. Now, the question is what will be your new xg star, let us say, as a result of this g has now moved, let us say, to another point here, g star. So, as a result of this, what is x g star? Okay. Now, it is equal to x g plus d into m 2 by m 1 plus m 2. Now, this is what you have to it will come now for the next derivation, that is why. So, just remember this thing, if a body is moved by, if it is moved by a distance d in a system, then the center of gravity will move by d into m 2 by m 1 plus m 2. Now, remember it does not exactly have to be mass all the time, it can be volume also, means x g does not have to be the center of mass, it can be the center of volume as well, it is the same concept, it will be d into v 2 by v 1 plus v 2, okay? It is exactly the same. Now, that we will need. So, it just states that if one of the components is moved in a certain direction, the center of gravity moves in the same direction, a distance equal to the change in moment divided by the total mass. This is the change in moment, this is the total mass. Okay. This we need for the next derivation, not this one, the one coming after that. Let us do this. Okay. Now, okay. Now, let us take a look at this figure, because it is easier to explain, show this than draw it. Now, again just like the is almost the same thing like we did in Archimedes principle, that is we now have a body like this, a body we have, and let us say the water plane and water line is given by this. This is the water line, okay, and what has happened is that with this point as this line x, let us call this x prime as axis of inclination, you are tilting the body very little, not much, but you are tilting the body a little, just like we have studied about the previous cases, I mean previous figures and all, we saw some inclinations, just like that the same healing is happening here. So, W 0 L 0 was the initial water line, this thick line is the initial water line, it has now moved to W phi L phi, okay, W phi L phi. Okay. So, this is the figure and this is the concept, and dA is a small area in that water plane, just remember that much. Now, let us assume that the body is not moving up or down, okay, it is just tilting, means that center is not changing, going up or down, it is just tilting. Therefore, whatever comes out must be going in on the other side. There is no change in volume as such, there is only a submergence and a emergence. One side is submerged, one side is emerged. Whatever volume goes in there, same volume comes out there, okay. Then, now the volume that goes in, why did I say whatever volume goes in there should be the volume come out? Why should it be? Exactly, it is coming because of the Archimedes principle, because the total volume cannot change, the weight of the body is not changing, and the body is not going up or down, that means that the buoyancy force is not changing. So, the total volume is not changing. So, whatever volume is going in must be the total volume that is coming out at the other side. Okay. Then let us assume that this horizontal, this and this is vertical, and this is z and this is x or y, let us call this y. So, this is initially W 0 L 0 and the body then tilted to. So, what is this W 0 L 0? It is the initial water plane, okay. Water plane is like this, and then means this is the water plane, it is like this, the water plane is like this, and then it tilted like this, and this is the water plane, and this distance I am this axis I am calling as y, this is z. Now, that is what we have drawn here in the 2 dimensional, we are drawing that y and z, and therefore, you have W 0 L 0 and W phi L phi. Let us assume that it is tilted by a small angle phi. Now, this distance let us call it as y, any point on the body, it is not any fixed point, any point on the body is called as at a distance y. So, this distance is now y tan phi, right. If that is phi, that is y tan phi. Is that correct? Yes. This is y tan phi by y is tan phi. Okay. Now, what will be the volume that now this side has gone out of the body and this side has submerged into the body, into the water. Okay. That is how it is defined. Now, V1 that has gone out is defined as dx dy, dx dy. Yes, do you see that? Why is it? It is actually z dx dy, that is a volume, z dx dy, and z is y tan phi, because we are seeing it from that figure. And similarly, this is the volume that has emerged, and V2 is the volume that has submerged. It will be minus, because y tan phi dx dy, and this is again z dx dy, this is what has submerged. Now, we are saying that V1 equals V2. Okay. Then what does it tell us? It tells us that I will just leave it here. Then now, I am taking the tan phi outside because it is not a part of dx dy. I can take it outside the integral. It is not a part of y either. It's not dependent on x or y or z. Okay. So, I take that phi outside, 2 and 2 tan phi I cancel out. So, what you see is that integral of y dx dy is 0. Now, what is yc? Means, what does this imply? That is y dx dy is equal to 0. The meaning of that is, what is yc is the centroid of the system. It is given by, how is it defined? It is defined as y dx dy. I think you will know this definition, right? You must be knowing this. I mean, it is just the same thing that center of mass, centroid, I am writing in a differential form. Instead of writing as x into a, x, like you can write like this now, y1 a1 plus y2 a2 divided by a1 plus a2. So, I am just writing it in the differential form. So, y dx dy integral divided by dx dy, that is the total area on the bottom. Now, what this implies is that, therefore, yc is equal to 0. Yc, the centroid, what this implies is that, now if a system rotates in this fashion with a small angle, two conditions: first, it is a small angle of inclination, and two, without going up or down, it just tilts slowly, and it tilts such that the volume immersed is equal to the volume submerged. It will be tilting about its centroid. Okay. That is what actually we have proved with this derivation. So, I will just read it. So, let the initial water plane be W0 L0 after an inclination where the volume of displacement is constant. That is important, where you have V1 equals V2. That will happen if the body is not going down or up. That means the center of the body, centroid of the body is not going up or down. It is just remaining at that point. And if it tilts with an angle phi, small angle phi, let us assume that the new water plane is at W phi L phi. Now, the axis of inclination will be a straight line always passing through the centroid of the water plane area. That is this concept will come in for something later. So, just right now we will just stop with this concept here. So, this concept is that it will pass through the water plane in such a case. So, it will pass through the centroid of the water plane in that case. Now, always when you have a ship, means if you have a ship like this, you know that if you have the water plane at some point where the water means water starts at that surface water plane, there will be a surface of the ship at that point, right. That is called the water plane area, I have already told you. Now, the centroid of that water plane area, somewhere between you will have the centroid of that water plane area, that is called a center of flotation. Okay. It is a very, very important term. It is the center of flotation, not center, let us call it centroid. Centroid of the water plane area. Centroid of the water plane area is known as center of flotation. That is what we have said. In such a case that a body is floating and it undergoes a tilt such that the whole volume does not change, only the volume that has emerged and submerged are different and they are equal. Whatever has emerged is equal to whatever is submerged, such that the total volume change is 0. When a body tilts in such a fashion, it is always tilting through its center of flotation. Okay. Its yc will be, it will always be through its yc, it will always be tilting about that. So, when it is healing, when these conditions hold, it will always be healing about that center of flotation. Actually, it is the same with trimming, but that is later, we will come to that later. Okay, that is one concept. Now, next one, we have to derive an expression for the metacentric radius. Now, again we have the same system as before, and let me draw this figure. So, let us say this is the metacenter M0. Now, initially this is the center of buoyancy B0. Now, due to the body has inclined a bit, as a result some volume has gone in, some volume has come out, and the center of buoyancy has shifted to the region where the volume has gone in, means where more volume has gone into the like if it is like this, it is tilted like this, more volume has come in here, that means buoyancy will shift here, center of buoyancy will shift here. That also they keep asking the why was this, how the center of buoyancy shifts. The only thing you have to know is what is the center of buoyancy. It means the centroid of the immersed volume. That means whatever volume is inside that immersed volume. Now, if I keep increasing the amount of volume on the right side, obviously the center of buoyancy will shift to the right side and other side like that. That is the center of buoyancy. Now, B0 to B5. So, obviously this is tilted there and it has gone to B0 to B5. Now, to really find B0, B5, we make a couple of assumptions, but I will tell you that is. So, first thing we need to find out is this YB, okay, how much has the coordinates of B0 to B5, it has shifted like this. Now, to get this value, you need to find out how much YB. What is YB? Means how much has the y coordinate shifted, okay? How much has B0, B5 shifted in the y direction? That YB we need to calculate first, and similarly we need to calculate this XB, YB and ZB, in fact all three of them. Then how to find that? Therefore, I will write here. Now, this is just like your previous problem where you shifted a mass from one point to another and you saw that the center of gravity shifted. Just like that, when what has happened here, a volume has changed, shifted, means the volume inside, there is a volume decrease there and there is a volume increase on the other, because the body has come like this, there is a volume decrease on this side and there is a volume increase on the other side. So, it is like a volume has shifted from one side to another, and as a result of it, what will be the change in B? It is exactly the similar same thing as, means if you had a mass here and you shifted the mass to here, what will be the change in G? We saw that from that small expression, that is we said that that change in G is d m1 by m1 plus m2, just like that, or it can be d v1 by v1 plus v2, it can be volume also, it is the same thing, just like that. So, that is what we are saying here, some volume here has gone, some volume here has come, volume has shifted, as a result of which you will have a d into v1 by v1 plus v2 will give you the total change in that that point of buoyancy, that yb, xb, zb, you will get like that. So, the change of coordinate will be given by the same expression, this is from that only I am taking, change of moment of volume, I just change the mass to volume here, change of moment of volume divided by the total volume. Okay. Now, the volume itself we have seen is given by integral, actually integral y, with this we have done in the previous definition, y dx dy, y tan phi represented z, and so it is z dx dy, integral of z dx dy. So, that z is, we have seen in that expression, this is y tan phi. So, y tan phi represents z. Okay. Therefore, what will be xb? It is this, the change in xb means the change in coordinate of the center of buoyancy due to that shift in volume. It is given by integral, I will just write it and then explain, xy tan phi dx dy divided by integral of y tan phi dx dy. This is the whole integral over the whole volume. Okay. So, this is equal to integral integral of x y tan phi dx dy divided by, what is this at the bottom? Here actually it is the whole integral, it is actually the total volume of under the submerged part. So, it is del. Okay. Now, this thing at the top, that is at the numerator, you see this x y tan phi dx dy is a moment of volume. Okay. X into volume, integral of x into volume, it is, so it is known as, we write it as x I y, it is called it is a moment of inertia. I think you have done moment of inertia, no? So, I actually cannot remember the exact definition for the moment of inertia. That is, it's do you remember, and if you remember, what is the exact definition for the moment of inertia as such? Moment of inertia is defined as moment of volume, I believe it should be a moment of volume or moment of mass, it does not matter. So, that is what this is, y tan phi dx dy is the volume, or if you multiply it by rho, it is the mass, that is okay, and multiplied with x and integrated, that will give you the moment of inertia. Okay. So, that is the moment of inertia, it is written as, so this is actually Ixy by del tan phi. So, oh, this is actually Ix by tan phi. Okay, this one. Then Yb will become volume y into y tan phi dx dy by del, which will become I by del tan phi. Now, it is also important that you remember some of the, means when you get this expression, some things you have to remember, like I mean what I remember I will tell you, like some moment of inertias you have to remember by heart. For example, that of a rectangle, like a circle, like for a rectangle when you have like this, let us assume that this is yes, this is, I mean, this is B, this is L, and let us suppose you are taking the moment of inertia about this axis. Okay. This is a longitudinal axis. Okay. Now, this is LB cube by 12. This is the moment of inertia. Okay. Remember, now remember, that is the moment of inertia. You have to know one thing, you have to know about which axis you are taking, that is very important in moment of inertia. So, in our case, in this case of tilting, the axis that we are always means this is the body, it is tilting like this, that means it is tilting about this axis. You have an axis like this and it is tilting like this about that axis. Okay. So, it is this axis, you are taking the moment of inertia about this axis and you are taking the moment of inertia of that water plane, means you have the surface which is on the water, that you are taking the moment of inertia of that shape about this axis, about the axis about which it is tilting. So, two things important in calculating this, and it is important. For example, if you are taking the moment of inertia of this figure about this axis, it will become the other way, it will become B L cube by 12. So, because that is important, it will change your answer. So, B L cube by 12 and L B cube by 12. Similarly, you have to remember for a sphere, these are the, I mean circle, these are the two things that we commonly use in this course, the problems. Pi d power 4 by 64. Okay. Yes, pi r, yes, pi d power 4 by 64. This is the equation for the circle moment of inertia, of course, about any axis. So, this is the moment of inertia of a circle, and this is for a rectangle. So, three figures you will need: circle, rectangle, and a square. All right. So, now this you have y b is equal to I by del tan phi. Now, let us assume that this now remember, in ships we are talking about heel angles never in excess of okay, I cannot say that, but in most cases in these derivations we are talking about heel angles not in excess of probably 10 degrees. Okay. It is not more than 10 degrees. You are not, of course, it is not that the ship cannot heel more than that, but in general you do not deal with that kind of heel angles like 50-60 degrees and all. Of course, when you draw when you derive the equations, we will see a static stability curve and all, you draw it for the whole ship from 0 to 90 degrees like fully tilted and all that, but it is not in practice. What you generally see because of wind and all that is 0 to 10 degrees or maybe 15 degrees maximum. So, in these cases you have, we say that phi is really small. So, these derivations that I am doing is only for ship. Okay. You cannot generally extend it for all types of bodies, all types of rectangular small bodies that tilt fully and all, you cannot extend this. But for the ship we can say that y b is equal to I by del tan phi. Now, you know that when phi is very small, tan phi can actually be written as phi itself. Okay. So, this can be written as like this. Now, I take this figure again. Now, again this is not an accurate derivation because this is true only if phi is very small. So, you can write as now let us assume that this is for very small this distance actually this ZB that you are talking about here is very small, it is not, it is very negligible, because of which you can really assume that YB means this distance is actually BM tan phi. Okay. Means this is phi, this is always phi. Okay. This is the angle through which the body has healed. So, BM tan phi, its slight of course assumption or slight approximation is there in this derivation, but it is okay. For ships it is not wrong, it is okay. So, therefore, BM tan phi YB is equal to this is equal to BM tan phi, or BM tan phi is again phi, okay, BM phi. Therefore, what do you get? You get that BM can be represented as I by del. this is an expression for the metacentric radius. Again, this is a very important concept. I will ask a very simple question related to this. Suppose you have a submarine, like going inside the water now fully. What will be I here? What did I define I to be? What is I? I is the moment of inertia of the area of what? Water plane. What is the water plane when a submarine is submerged? 0. There is no water plane area. Therefore, I is 0 for a submerged body. I mean, for a submarine, I is 0. Therefore, you have Bm equal to 0. So, this again is a usual question. They ask for a submarine everywhere. In interview also, they will ask you this question. Means job interviews, they ask this. In case of a submarine, nothing else will be given. In case of a submarine, what will be your Bm? So, you just first thing you do is you say that Bm is equal to I by del. And in case of submarine, in case it is under the water, of course, in case it is fully submerged, then Bm, there is no I, there is no water plane, there is no such area, as a result of which I becomes 0 and therefore Bm becomes 0. Okay. All right. Now, we have to see how to apply this. We will take a problem. Now, I will just, okay, before I do that, I will just summarize couple of things. There are some important, we have actually covered quite a bit of formulas today. So, we will I'll just write some important things that we have covered. First thing we covered is the Archimedes principle, which states that delta, which is equal to rho into del, or sometimes it is written as gamma into del also, in which case delta represents the weight and in this case it represents the mass. So, rho into del is equal to the weight of the body. Okay. This is the first thing which we covered today, which can be written as so. This is the same thing, that is the total weight of the body is given by gamma Cb into LBT. So, just so that you remember this, how Cb is connected to del, that is all. So, that is the first thing. Then the next important point that we talked about is about how you tilt the water line instead of the body itself. That is one important thing. So, you never tilt the body as such, that drawing you will never see such thing, you just like we have shown drawings here, always the water line is tilted. So, the important point is that the water line is always horizontal, another important point related to that, water line is always horizontal. So, the G, from G the weight acting is always vertical. So, that also you have to remember. Then the condition for statical stability is that this is another important point that we mentioned today, that is that Gm should be always greater than 0. Okay. Then next thing is that, so these are important things you have to remember from today's lecture. Gm is equal to this thing Kb plus Bm minus Kg. So, this equation also you have to remember because it will be important in doing problems. What I do not think we will do the problem today, we will do it next class. So, that so to do that, this of course you do not have to memorize it. In fact, if you just look at this, you draw that m, you can derive this instantly, but some other things you have to remember, like this expression. This is probably a little more complicated than the other expressions. Other things you can just remember it from the class itself. This you study the derivation and remember that Bm is equal to I by del. Remember that is an important point. So, I think these are the important things to take away from today's class. And and again I repeat one more point is this about this I is actually the, again I repeat, it is the moment of inertia of that water plane area. Again water plane area means the area that is exposed at the surface, that area that is that interface between the water and air, that intersection is that intersection area. Like for a ship, you have a ship like this, that where the water is there, that area, okay, that area you have, and you take the moment of inertia of that area about which axis, that axis is the axis about which it is tilting. If it is tilting like this, you are talking about this axis, and it is that area. So once you know these two, you know I, and you can calculate Bm, and once you calculate Bm, you can calculate Gm using these formulas. Kb, remember, is the center of buoyancy. K is fixed, okay, that is always 0. Now B is where the center of buoyancy occurs, that is again you know how to calculate it. It is the centroid of the immersed volume. Kg is the centroid of the total weight on the ship. So once you have that, you can do this, okay. So I think we will continue next class. Okay, thank you.